Hi everyone, today we're going to start 11.7, which is kind of stems from the fundamental counting principle, but we're going to talk specifically about something called permutations. So if you'll remember, the counting principle is when you have two different experiments, we'll call them M and N, and as long as they have distinct outcomes, if you want to find the total number of outcomes, you would just multiply m times n. So for example, if you had your first outcome was that you flipped a coin, we know that we've got heads and tails, so that's two outcomes. And let's say you rolled a die that's six-sided, you would have six outcomes. So if I want to find the total number of outcomes, if you were to do both experiments, you would just multiply 2 times 3, 2 times 6. So there would be a total of 12 different outcomes. Okay, let's look at an example. So we have a license plate, and every license plate has numbers, and it consists of two uppercase letters followed by 4 digits. Determine how many different license plate numbers are possible if repetition of letters and digits is permitted. So I can repeat. So we've got 6 different spaces for our letters and numbers, and it says that it consists of 2 uppercase letters. So we'll let the first 2 be the letters, and then it's 4 digits. So these have to be numbers. If I am looking at letters, how many possible letters could I choose from for my license plate? Well, there's 26 letters in the alphabet, so I have 26 different choices. You can repeat letters and digits, so that means I can reuse the same letter, so I still have 26 choices. Now when we're dealing with numbers, it's 0 through 9, so that's 10 different numbers. So I've got 10 for the first to choose from, 10 for the second, 10 for the third, and 10 for the fourth. And I'm using the counting principle, or a form of it, where I'm just going to end up multiplying all 6 of these numbers together. So when you do that, you'll end up with 6,760,000. So that's a lot of different license plate numbers, and they're all different. Now, what happens if you can't repeat letters and digits? So again, we'll start out with our 2 letters and our 4 numbers. So this time when I start out with the letters, I've got 26 to choose from, but you can't repeat. So whatever letter you chose, now there's 1 less. So I only have 25 to choose from. And the same is going to work for the numbers. I've got 10 to choose from the first time, but every time I use a number, I can't reuse it. So I only have 9 to choose from for that spot, and then 8 to choose from for that one, and then 7 that are left to choose from for the last spot. And the counting principle tells me I'm going to multiply all these together, and when I do that, I end up with 3,276,000. What if I start putting some restrictions? So the first letter must be a vowel, and the first digit cannot be a 0. And repetitions of letters and digits are not permitted this time. So I know now that I've got my 6 spaces. This first one has to be a vowel. And it tells me that the first number cannot be 0. And I'm also not allowed to repeat. So I've got 5 vowels, A, E, I, O, U, to choose from for the first space. The second space has to be a letter, but one of those letters was used. It was just a vowel though. So now I have 25 letters to choose from. Remember, I'm not allowed to repeat. In the first spot for my numbers, I can't use 0, so that means that instead of choosing from 10, I've got 9 digits. Now for the second spot, there's still 9 numbers that are left since you couldn't use 0 for the first, And that means you can use it now for the second one. So whatever number I chose for that first number spot where the 9 is, it couldn't have been 0, but now 0 gets thrown back into the mix. So I've got 9 to choose from again, and then 8 and 7. And when you multiply all 6 of these numbers together, you end up with 567,000. Okay, you can pause the video and try these 3 problems on your own, and then unpause when you're ready to talk about them. At Old Navy, a supply of solid colored t-shirts has just been received. The t-shirts come in the following colors: green, blue, white, yellow, and red. Preston, the floor manager, decides to display one of each color t-shirt in a row on a shelf. In how many different ways can he display the 5 different color t-shirts on a shelf? So we've got 5 different colors, and he wants to display one of each color t-shirt. So when he displays the first color, he's going to have 5 to choose from. Once he displays that color, then he's going to have 4 left to choose from. And then 3, and so on, all the way down to 1. And when you multiply all of those together, 5 times 4 times 3 times 2 times 1, you end up with 120. So there's 120 different ways he can display the 5 different colored t-shirts on a shelf. If he wants to place the blue t-shirt in the middle, how many different ways can he arrange the t-shirts? So we've got our 5 different t-shirt colors. In the middle has to be blue. So there's only one way that I could put the blue there. Since I already used blue, that leaves me with 4 colors to choose from for the first spot, 3 to choose from for the second, 2 to choose from for the fourth spot, and then 1 that's left at the end, whatever color I didn't use. And when you multiply all those together, you get 24 different ways. So when we start restricting, you can see that you have a lot less ways that you can arrange things. So in this case, the order begins to matter. If Preston wants the white t-shirt to be the first t-shirt and the blue t-shirt to be the last, and how many different ways can he arrange the t-shirts? So if white has to go first, there's only one way to put white. And blue has to go last. There's only one way to put blue. I just used 2 different colors, so that means now there's only 3 left to choose from for the second spot, 2 to choose from for the third, and then whatever color you didn't choose, that's the only one left over. So it's 1 times 3 times 2 times 1 times 1, which comes out to 6. Okay, let's look at one more example. Many garage doors come equipped with a keypad that allows residents to open the garage door by entering a 4-digit code. Repetitions of digits in the code is allowed. The first question says, how many different 4-digit codes are possible? So again, we're dealing with numbers, and you have the numbers 0 through 9. So you can count, that's 10 different numbers. You can repeat them, so you have 10 to choose from for the first, 10 to choose from for the second, and so on. And then we're going to multiply all of those together, and that's just a 1 with 4 zeros. So there's 10,000 ways. So next time you try to pick a code, you can think of all the possible ways that you can do it, and it makes it very difficult for people to try to decipher the code or hack it. Although people are getting better at that now. So that's why we have, they're increasing the number of digits you can use for your passcode to get into your phone, or you have like this 2-factor authentication now to get into things. It's because hackers are figuring out ways to determine codes, and it is what we're doing right now. It's the counting principle, and they're looking at cryptography and number theory. Okay, so my next question is, if one of these codes is randomly selected, What is the probability that the code has no repeated digits? Okay, so I'm looking for the probability of no repeated digits. So that's going to be the number of codes with no repeated digits over the total possible, which is our definition of probability. Okay, so let's think about this. We know that if you can repeat digits, there's 10,000 possible ways to do that. So that's going to be my denominator. My numerator, on the other hand, is when I can't repeat. So if I can't repeat digits, that means for the 4-digit code, I've got 10 to choose from for the first, and then once I use that digit, I can't repeat it. I've got 9 for the second, 8 for the third, and then 7 for the fourth. And if you multiply all those together, the numerator on top gives you 5040, and the denominator is 10,000. And that's a big number to reduce. So we're just going to divide, and it comes out to 0.504. So if you think of that as like a percentage, that would be about 50%. So the probability, there's a 50% probability that the code has no repeated digits. So as you saw through in some of the examples, there were examples where the order didn't matter. So when we looked at the first problem, when you could repeat letters and digits, and it didn't matter the order that we put them in. All it says is that the license plate consisted of 2 uppercase letters and then 4 digits. In this next problem here, it told us about the colors. So in the first one, it says, and how many different ways can he display the 5 different colors? It didn't give us a specific order. But then as we started doing some of the other problems, we realized that the order started to matter because they had to have the blue t-shirt in the middle in the one problem, and then in the third problem, they had to have the white t-shirt come first and the blue come last. So the order began to matter. When the order matters, we have what's called a permutation, which is any ordered arrangement of a given set of objects. Okay, and what you always need to do is assume that repetition is not permitted. They will state in the directions if it is. So otherwise, assume that you can't repeat. The number of permutations of n distinct items, so remember n just means any number, it could be 7 distinct items or 10 distinct items or 1,000, is what's called n factorial. And n factorial is this exclamation point at the end. In math, what that means is if I was to take a number, say like 3 factorial, that just means it's 3 times all the numbers that precede it. So times 2 times 1. So 3 factorial is actually equal to 3 times 2 times 1, which is 6. Another example I gave you was 4 factorial. So that's just the number 4 times all its preceding numbers, times 3 times 2 times 1. There are calculators, scientific ones, that have the factorial symbol on them, and it makes it easy to multiply those numbers out. Okay, let's look at an example of when we would use permutations. So Sumiko works at an animal shelter that has 7 cats available for adoption. Sumiko is preparing a poster that will feature a photograph of each of the 7 cats. The first question says, how many different arrangements of the 7 photographs are possible? So the first thing you want to ask yourself is, does the order matter here? And since we're looking at different arrangements of 7 photographs, no, the order doesn't matter. It doesn't specify they need to be in a specific order. So this is not a permutation. This is just what we did earlier. So you think of it as like you've got 7 places to put the photographs. In the first spot, you've got 7 choices to choose a photograph. And then in the second spot, now you have 6 places. And in the third, it's 5. And if I keep multiplying, you end up with 7 factorial different ways. So that's just 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you multiply that out, you actually end up getting 5,040. So that's a lot of ways that you could arrange those 7 pictures on the wall or in a poster. We did a problem similar to that, except we didn't call it a factorial. This one right here, 5 times 4 times 3 times 2 times 1. That's actually 5 factorial. And how many different ways could Preston, the manager, display the 5 different colored t-shirts on a shelf? There's 5 factorial ways. Okay, because the order does not matter yet. In the next problem, if one of these arrangements of photographs is randomly selected, now we're looking for what's the probability that the photographs are in alphabetical order by the cat's names. Assume the cats all have different names. Okay, so if they all have different names, the probability that the photographs are in alphabetical order, there's only one way to do that out of 5,040. Because every cat has an equal chance of being placed first, but it depends on the letter of their name and where it falls in the alphabet. So there's 1 out of 5,040 ways. You can pause the video and try the next problem on your own, and then unpause it and when you're ready to go over it. So consider the 5 letters A, B, C, D, E. And how many distinct ways can 3 letters be selected and arranged if repetition is not allowed? So again, ask yourself, does the order matter here? And the answer is no. It's just saying in how many different ways can 3 letters be selected and arranged. So you've got 3 letters, A, B, C, D, E. That's 5 letters. So you have 3 of them that you're choosing. For the first spot, you've got 5 letters to choose from, and you can't repeat. So now you only have 4 to choose from for the second, and then 3 to choose from for the third. So that's 5 times 4 times 3, which comes out to 60. So for instance, if I take those 5 letters and I start arranging them, you could have B-A-D, you could have D-A-B, E-C-A, C-D-E, A-B-C, blah, blah, blah. So there are actually 60 different ways you could pick any 3 letters and rearrange them out of 5. So let's look at a permutation where the order actually matters. There is a symbol that we use, and it's this right here. And you actually read it, you would say N choose R. And it's a permutation where you have R objects selected from N objects. So if we think of sets, right, N would be the bigger set. And from N, we take smaller sets, R. So think of N as your set, your universal set, and R is a subset, so it's a smaller set. So R will always be smaller than N. In the example, it says the fishing club at Valencia Community College has 9 members. To determine club officers, 9 slips of paper, each containing the name of a member, are placed into a hat. The club advisor randomly selects a first name from the hat to become the president, a second name to become secretary, and a third name to become treasurer. How many different arrangements of club officers are possible? So personally, I think that's a very unfair way, but that is how this club is decided to pick president and secretary and treasurer. So the first thing you want to ask yourself is, does the order matter? And here the answer is yes, because whoever you're picking first is automatically the president, and whoever you're picking second is automatically the secretary, and so on. Okay, so the order does matter. So I need to figure out what n is and what r is. So n in this problem is the number of objects. So total, we've got 9 slips of paper, each representing a different name. And it says the club advisor randomly selects a first name, a second name, and a third name. So they're selecting R objects, 3 objects. Remember, R will always be smaller than N. So I'm looking for the permutation of 9, choose 3. So on the top, my formula says take n factorial. N here is 9, so I'm going to do 9 factorial over n minus r factorial. So 9 minus 3 factorial. So if I simplify, 9 minus 3 is 6. So I end up with 9 factorial over 6 factorial. Remember that 9 factorial just means 9 times 8 times 7 times 6 times 5 and so on. So what I'm going to do to simplify this is I'm going to start writing out 9 factorial, but I'm going to stop at 6 for a second, and I'm going to put a factorial there. Because remember, 6 factorial just implies 6 times 5 times 4 times 3 times 2 times 1. So really, this part right here represents the rest of 9 factorial. But the reason I'm doing that is because now what I can do is cancel the 6 factorials out. So all I have to multiply now is 9 times 8 times 7. And when you do that, you get 504. So there's 504 different ways that the club officers can be picked. Okay, try this one on your own. The Orlando Bicycle Club has 10 different routes that members wish to travel exactly once, but they have only 6 specific dates for their trips. In how many ways can the different routes be assigned to the dates scheduled for their trips? Does the order matter here? And the answer is yes, there's 10 different routes, but there's only 6 specific dates. The order matters. So here n is going to be 10, and r in this case is 6. So we have a permutation, 10, choose 6. So my formula is do n factorial over n minus r factorial. So I end up with 10 factorial over 4 factorial. And you're going to do the same thing. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial, which is just 4 times 3 times 2 times 1. And I stopped at 4 factorial so I could cancel those 2 factorials out. And then you're going to need a calculator to multiply those numbers together. 10 times 9 times 8 times 7 times 6 times 5. And you end up with 151,200. How else could you have worked out the above example? So pause for a second, think what else you could have done and why. If you thought about using the counting principle, you're correct. Because this is what we did earlier. You think about you have 6 specific dates and 10 different routes to choose from. So think of it as here's your 6 different dates. You've got 10 to choose from for the first, 9 to choose from for the second, and so on. So what do? Just multiply those together and you get the same number. So we used here the fundamental counting principle. I mean, if you really think about it, it's m times n distinct objects. What happens now if you have duplicate items? So, maybe 2 letters that repeat or 2 numbers that repeat in a word, for instance. So up until this point, all the examples we've discussed have involved arrangements with distinct items. They keep using that word. Distinct just means different, right? What happens if we have a permutation in which some of the items to be arranged are duplicate? So for example, if you have the word dad, It contains 3 letters, but 2 D's are duplicates. How many permutations of the letters in the name Dad are possible? So it depends on how you look at it. If I was to just look at it using the 3 black letters there, D-A-D, right? I could arrange it like this. I could arrange it like that. Sorry. I could also arrange it like this. So 3 different ways. That's it. So that would be if you can't distinguish the 2 D's, like if there's nothing different about them. So we'll say if they're not distinguishable, if you can't tell them apart. But now what if I change colors and I was to make the first D, I'll keep it blue, and then let's say the second D, I'll make red. Now what I can do is I can switch these all around. So I can change the order, and now you can see it's different. So I can do that for all these different combinations. And now I end up with a lot more. And you'll have to bear with me here while I change my letters color. So now we've got 6 if the D's were distinguishable. So in other words, if you can tell them apart. So typically you won't be able to tell them apart. So there's a formula we can use. And the formula says the number of distinct permutations of n objects where n1 of the objects are identical and n2 of the objects are identical. N of the objects are identical is determined by using n factorial over n1 factorial times n2 factorial and so on. So what this means is here I have the letter D, there's 2 D's. And I've got 3 letters. So it would be 3 factorial over 2 factorial, the 2 factorial representing the 2 D's that are repeated. So remember, 3 factorial just means 3 times 2 times 1. And 2 times 1 I could just put as 2 factorial. So the 2 factorials will cancel and you'll be left with just 3 different ways. So if we take the word Cincinnati, and how many different ways can the letters of the word Cincinnati be arranged? So when I go through and look at this, I notice that I've got 10 letters. And when I scan this really quick, I see that it has 3 I's. And I see 2 N's and 2 C's. Sorry, there's actually 3 N's. 3 N's and 2 C's. So to figure this out, the formula says just take the number of items, so there's 10 letters, so it's 10 factorial, and put it over all of these guys' factorials and multiply them. So it's going to be 3 factorial times 3 factorial times 2 factorial. So I can do something like this quickly in my head. 3 factorial is 3 times 2 times 1. So 3 factorial is just 6 times 6 times 2 factorial is 2 times 1, 2. 6 times 6 times 2 gives me 72. So it's just 10 factorial over 72. And you'll need a calculator to figure that out. And if you type that in, you get 50,400. By the way, if you need a calculator that will do permutations, Desmos is a free app that you can use that's very helpful for things like this. You'll definitely want a scientific calculator that can handle permutations, though, for the test. In how many ways can the letters in the word statistics be arranged? So take a second, pause this, see if you can try it on your own, and then you can work it out with me. So here, the first thing I notice is, again, there's 10 letters. So it's coincidental. They don't always have 10 letters. You've got 10 letters, and it actually is even stranger. There's 3 S's, there's 3 T's, and there's 2 I's. So it's just like the last problem. It comes out to be 10 factorial over 3 factorial times 3 factorial times 2 factorial, which we already know the answer is 50,400. Okay, if you have any questions with this section, please reach out to me. Definitely start the homework, make sure you're all caught up on it, and I'm here if you need me. Hope you all enjoy the rest of your day or night.